All right, can you guys hear me? We're going fast enough? Okay, we're on schedule. Okay, in this set of slides, example 3 and 4 are very closely related, but they're numbered 3 and 4. It's code 3 and 4, so we keep the numbers consistent. And then a new kind of example. Okay, so in this example, seeing two cars, or really seeing the same car twice. And it was inspired by this video, which I highly recommend that you watch later because it's a really cool video on saccadic masking. As you're watching something, how things can slip in between in your blind spot, as you think you're looking for cars and you don't see them, and then you don't see the motorcycle, and then of course bad things happen. So in our physical model, I'm going to assume your two eyes are looking at the car at time equals 0, and then later at time equals 2. And here again, we need weight because we have angles and distances in the same problem. Really, it's two completely separate problems, but leave that in the back of your mind. We run this problem, and what do we get? So first of all, I'm going to start here putting I'm putting the cars in random places, or quasi-random places, but they really belong at these two locations. And so I run the code, can't change, meaning these are the angles observed by your two eyeballs. And then the consistency radius started at 2.7. Then we optimized and we got back to -5, 15, 10, 5. That's good. And these, of course, didn't change. And then we have a low consistency radius. Good, we win. Great. But then I try another one where I move the guys too far away. So this is an example of how you can see this thing blow up. The consistency radius went down. So what happened? So here's where your eyeballs are. Your eyeballs are at plus and minus 1 down here in this yellow spot. And here's where I wanted it to converge to. That's where the solution works. And then I started off the first view here and the second view here. So why it ended up there, I don't know. I have no idea. But do notice that the angles are the same, right? So it's basically like instead of seeing a large car move slowly near you, you're seeing a very tiny car move, like it looks in the distance. So like in real life, you would have more information. You would know that what the size of the car is. But in this simplified model, it converged on something that was quite plausible, actually. All right, so now let me try another one. And I just made these two graphs roughly the same size so you can get a sense of scale. The eyeballs are still down here. I started both of the initial ones over here, kind of close to the solution, and they converge just fine. So that's just sort of a little bit of gut instinct about you can't really start too far away. What does that mean? I don't know. It'll be different for your problem. But that means if you're not getting convergence, try moving your guesses around. You may find a sweet spot and converge. Okay. So in some situations, the consistency radius can only go down so far, like in least squares regression. You're not going to get a perfect line unless you have a collinear data. But sometimes the only clue you're going to get is a consistency radius that's not as good as you wanted. That may be the only clue you get. If you were expecting it to be 0 and it's not quite, maybe you're really far off. Who knows? Okay, so but what did we really want? What I really wanted was this, which is much more in the tone of what we've been doing here this week, is the reason why I want the car to be at t equals 0 and 2 is so I can drop 1 in at t equals 1. At t equals 1, your eye doesn't see the car at all, but your brain sees the car. Where does your brain think the car is at t equals 1, given that you saw the car at t equals 1, t equals 0 and t equals 2? So how would we code this? So I sat there, this is one I just struggled a lot with. And I thought, how would I bring that data over? And because the way I'm thinking is, what's an arrow? I want the data to come together into that car in the middle. And I kept trying and I couldn't do it. I'm like very frustrated. And how do we get path independence anyway? And so what Michael recommended, and I'm like, I don't like that. But this would have been totally fine. He said, like, why don't you just give each of the cars a velocity? And I'm like, well, what if I don't have a velocity? Then I can't do that. And he's like, good point. But if you do have the velocity on each car, then you would get path independence because you would look at this car and notice how fast it's going, and then you can predict where it's going to be a second later. If you saw the car and its velocity is a second, you could reverse engineer that, and then you would have path independence, and that whole model would work just fine. But I'm like, no, I'm not. I don't have that data. I'm just making this up. I mean, that really happened. But I mean, I'm just making up my problem. I'm making up my own problem, and I want to follow it through to fruition. Okay, so I said, well, what about if I put all my data in what I call a headquarters node? So I don't have all the sheaf terminology he has. I can call it, span, whatever. I'm just going to call it headquarters. Okay, I'm going to put all my data in here, and then I'm just going to serve it out as necessary. I'm going to tell the eyeballs, this is what you're seeing, and I'm going to tell the cars, this is where you are. So actually, there's a solid theoretical explanation, which he's going to go into, about why I ended up needing to do that. It's not really cheating. I was like, this is cheating. He's like, no, actually, you had to do that. I'm like, what? Why didn't you tell me? He's like, well, because I wanted you to put velocities on. So no, so the theoretical underpinnings are not always necessary for you to understand as long as you do the right thing. And so your instinct may drive you to do something, and this worked. And so you can call this conglomerate data that I'm calling headquarters. It's like a Python tuple or a categorical product. Call it whatever you like. That's where all your data live. It gets farmed out. And it's actually a closure on the sets is what's being created. And then he spent an hour explaining, and I was like, forget it. Sorry. Okay, so this is what's in my headquarters node when I start. I just started with all zeros, and I just gave these random values of where I think the cars might be. They were just BS. But this is the part that doesn't change, is the angles at which you're seeing the cars. I took them from the last problem, and I had a bad consistency radius, bad because we got a good one down below. After I ran the code, I got everything exactly the way I wanted it. Was able to figure out where the car was at time equals 0 and 2, just like I did in the previous example. But now I can infer where the car is halfway between. Make sense? Okay, and then you can go look at the code and see how I did that, because the idea is you're not using angles to find the car in the middle. You're now averaging the two distances between the other two cars. Okay, new and different example. So at this point, I've been doing these examples, and I'm like, but they're all stars. I want to see something that isn't just a star, because that's kind of pathetic. And so I'm like, okay, not that we're not going to see more stars. We will see more stars today. But I wanted to move away from just seeing always a node in the middle pushing out data. That's too simplistic. So I said, okay, why don't we do a circuit example? Because he said this would make more sense. It would give me some more complexity. So I said, okay, let me just hook together. Let's say you don't know what circuits look like. So mini tutorial, this guy is an AND gate. This guy is a NOT gate. This guy is an OR gate. Trues are 1, falses are 0. So true is logic high. So there's electrons going through. And then 0 is logic low, not really 0, but close to 0. The AND gate means if both of those lines have electrons in them, then you get electrons out here. The NOT gate inverts it. So if there's electrons, it shuts them down. But if there's no electrons, they start going through. Of course, you have to power that thing, but never mind. Okay, and then this thing is an OR gate that either one, the electrons from either one are enough to open the gate, and you go through. Okay. So here's just one example. There's 8 possible ways you could set, there's 8 possible ways you could set A, B, and C, and then you can draw that whole thing out. And the messy part is the thinking. Thinking. What am I going to do? So what did we say? Go back to first principles. We said nodes require sets. So they've got to have circles with sets on them. Arrows require functions. It could just be what's called a projection from a tuple. What does that mean? You could have like a library of data, and then you just take a piece and you farm it out. That's okay. That's a function. My students hate that when I say, okay, we have a function of x and y and z, but we're only going to use x. Function of x, y, and z is x squared. Where did the y and the z go? Who cares? It's not part of this function. It's not part of this complete purpose. So anyway, you can have a function of 3 variables and throw out more variables. That's fine. A projection only takes one of them and hands it off. So it's like a library function. Okay. So we're concerned about consistency. We're not concerned about the logical flow of the data or where the electrons are going over time. And this is why I love this example, because I want the data to go this way. And that's not the way they go. That's the way the electrons go. That's not the way the data go. You see? You got to flip your logic on its head and say, what do you mean about the flow of data? It's not the flow of the electrons in the model. Okay, so the set 0, 1 is the entire set of Boolean options, true, false, high, low, whatever you want to call it. That is the entire set. So that is going to go on each node. But he says you need a symbol for that or not. I'm like, I want a symbol for that. I don't want to write curly braces 0, 1 all day long. I'm like, I'm making a happy face. That's me. I always put happy face. You'll see. So a happy face means you can pick 0 or 1. Okay. Oh, we're going to break this down. So if you're sitting at and, you're sitting in that node, you're going to farm off the x in one direction, the y in the other direction, and the and of the two in the other direction. It's like a mini headquarters node. It's like a little bit of control there. The or is going to work the same way, but it's going to spit out an or. Opposites are going to sit there. It's going to farm a 1 out in one direction and a 0 out in the other direction. Either way. That's how you put them all together. So what you do is you put happy face squared, which means just the Cartesian product of two happy faces. So that means for the data on that node, you get 0, 0, or 0, 1, or 1, 0, or 1, 1. There's only 4 options. So that's happy face squared. It's one of those 4 options. The happy face is either a 0 or a 1. I'm so glad you're happy. And so the projection 1 just means we're taking the first coordinate and pushing it out there, taking the, the second part of your happy face squared and pushing it there. You're anding them and pushing out this way. This guy, the or works the same way. And this guy is just pushing out, and we're combining. We're just, instead of pushing out the first element, we're negating that. We're doing 2 steps in one, which is fine. It's very easy to do. You'll see it in the code. You could have made another node to do that, but it's extra work. Okay, and it worked. It worked just fine. And so again, these things are whatever you want. Those are the things I decided. You could flip this, but when I ran it this time, A, B, and C couldn't change. And just because these are all 0s or 1s, I set them all to be 0.5 so that I was hoping they would slide away from 0.5 to either 0 or 1. Question, go ahead.
Sorry, can you go to probably I'm missing something, but how do I read the and2 and or and p?
This is the and gate, really. And so inside here, it's kind of like a mini.
No, and2. Sorry, the
okay.
or gate.
Okay. So this is a mini headquarters, and it's holding 2 Booleans. The first one and the second one.
Oh, okay. Sorry.
And so the second Boolean just goes to C. The first Boolean gets negated on the way. And then you or those 2 and you push
and I put the result there. Yeah, okay.
Yeah. Okay. So we ran it. It worked. Great. No problem. And so the one thing you notice is all these I set to 0.5. And then they actually went somewhere. So it went to 1, 0, 0, 0, 1, 0, 0. You got to look like 1.4 is not 0, right? You got to look at the exponent. You got to train your eye to look at the exponent first and then look at the content. Yeah. Because we just had it in the original diagram, there was a NOT gate there. So if you take out the NOT gate, you wouldn't. Okay, so here's all 8 combinations, and in your breakout groups, if you want, you can play with that and see that the code works. If you just change A, B, and C. I actually did this on a spreadsheet. So the reason it's duplicated is because I just put them in alphabetical order over there. They're exactly the same here, but here I was building it to see what N1 and N2 would look like. I wanted to be sure I wasn't making any clerical errors. So I did it on a spreadsheet, and that crazy spreadsheet writes 0, 1 when I mean 1. So just ignore the others. This is just a spreadsheet thing. Okay, but that's just as a check to see. All right, so, but surprise, you might think that it will be easier to only use 0s and 1s and to add up the number of times you see an error, but that doesn't work. If you did that, your code would successfully tell you when you were sitting on a solution, but you wouldn't be able to converge there. And that is something we will continue talking about why that happens. As these were developing, with talking them over with Michael, I would give another example, and if I have more questions, let's build another example to address those questions. And there were things that were just not settled even until, I would say maybe about 3 weeks ago, 4 weeks ago, well, fairly recently in my mind. And I was like, what kind of problems can you and can you not do with this? And I said, you tell me you can do anything with sheaves. And then I asked you a question, and you were like, well, that one wouldn't be a good example. I'm like, really? Well, then can you tell me which ones are good examples and which ones are bad examples? And he's like, no. So we finally got to an answer to that. Like, I'm sorry, I'm telling all you secrets. Okay, we'll bring it up again. This one you can practice if you like, and there's a hint. You can look at the hint or ignore the hint if you want to see how I structured it. Okay, so that's whatever level of hint you want. If you want the happy face hint, use it, and if you want to do it without from scratch, you can. Main concepts in these slides is that path independence really matters. Remember, we couldn't get to that middle car from each eyeball. We had to do something to preserve path independence. So we either had to put a velocity on each car, or we had to use some other structure to make sure all that worked. You cannot combine things from two sources into a single node. It has to be two paths are different paths that take you to the same place. So it could be a different mechanism, but they both have to take you to the same place. Okay, so that's hard to sort of wrap your head around because that's not the way we normally use points and arrows in our head, the way we normally write on paper. We can use other nodes to host data, the ones I call little headquarter nodes or mini headquarters. We need to think differently about the flow of information. It's not time dependent. It's not the electrons flowing through the model. It's a question of consistency of the whole system. And so this stuff kind of comes from these headquartery, like these nodes where the data kind of collect up and then spread out. So it's a different way of thinking. And we find ourselves, for some reason, we'd rather use real valued numbers, even if it's a Boolean question. Why? To be continued.
Right. So what we're planning on doing. It's 11 o'clock right now. What we're planning on doing is taking a 15-minute break. And if you are interested in doing computation versus not, theme the breakout groups today versus computational or not. You can put your name in one of those two columns if you have a preference. We'll see you in 11:15.
Thank you. So I have a lot of questions about how to apply this to IIT. One, of course, I can see an application in just having sheaf help translate between cause effect structures and phenomenology and qualia structures. That's all fine. Even maybe comparing cause effect structures, that's also fine. But this idea of optimization that you've been talking about, it's very new to me. I didn't know about that before. And I was thinking, and I would ask Renzo to chime in if he has some ideas, or anybody else, of course. There's at least two places where in the IT computations, I think we could use some optimization, some help, just to reduce computational power. So one, these are all half-baked thoughts, of course. So pardon if they are not superficial, but in the smiley face example, I thought, well, that really looks like a system of logic gates where I have some AND gates, some OR gates. And it seems to me what you were trying to optimize was, well, let's say I know the state of some of the gates, but not the state of the whole system. And can I figure out without actually going there and perturbing and observing?
Precisely.
And this, of course, can be immensely useful because sometimes in IIT, all the computations start from a TPM, from a transition probability matrix, and I need to know the TPM of the full system and perturb it in all possible states to then do my computations. So this can be demanding if I have a big system. So is that correct that we can use this to get a TPM?
That is absolutely something.
Awesome. The second question could be, let's say, now that I have TPM, I want to compute the cause effect structure, right? Which means that I have to compute distinctions and relations. And now I'm wondering, can I use the optimization in the sense that I compute only, let's say, some first order mechanisms and maybe the top order mechanism, and then I can infer more things. Yes,
this is subtle. This is subtle. And actually, one of the theorems I flipped up briefly that you didn't go into is the following. If you know the graph structure of that partial order, then you can optimize the functionals. That will be well defined because the consistency radius is a continuous function of those. Finding a graph structure, on the other hand, is not something that seems to be as well defined. effectively, then what you're trying to do is you're trying to reverse engineer what that cause and effect structure was. And if you read Judea Pearl carefully, he cautions against doing this in an automated way. And it is for this reason, as far as I can tell, is that there is a lack of continuity there. And if you look in the math community, there is a massive edifice of singularity theory, which is designed to try to understand the kinds of topological changes that can occur as you're trying to look at functions of these. And this is the sort of thing that is field metal quality still. So very hard.
Can I add one follow-up question quickly?
Yeah, let's move on.
I think I'm a little slow on understanding this, but just to clarify, in the sheaf, you're kind of a priori deciding what your restriction function would be. Is that correct?
In all of our examples, we are doing that. What I just said is, if you happen to know where there should be a restriction function, you may be able to reverse engineer what that is from that. Because that is effectively a machine learning problem.
Right. So I guess I'm confused on, so in most like modeling, like not sheaf modeling problems, you're looking at the data, and then based on the data, you're fitting some kind of model that explains the variability in the data. And so if we're already making that function from the data and then putting that into the sheaf, that and then trying to predict what the source latent variable would be, isn't that kind of like confirmatory?
Yeah, seems that way, right? So here's the thing to think about. Again, echoing Judea Pearl. If you know what the high level structure, the diagram is, but you don't know the functions. If you have a finer, more subdivided diagram, more vertices, more edges, the models will tend to be more local. And that actually a lot more meaningful. The typical way that machine learning works is I'm going to take the entire data set and put it into a massive regression and try to fit that. This allows you to say, no, I'm going to do lots of little regressions that are actually more meaningful, easier to interpret. If I do the massive regression, I have 1,000 variables, I don't know what they all mean. And furthermore, I end up with coefficients on some neural network or some splines or whatever. I don't know what they mean. They're hard to interpret. Whereas here, you end up with handfuls of coefficients that are kind of spread out. And you're able then to isolate when you look at the consistency radius. You can see, where is it good? Where is it good? So it's fundamentally similar in that regard, but it gives you more control in how the model runs.
Okay, I can take only those who haven't asked a question.